Okay, um, this is Advanced Physiology. We're finishing up the cardiovascular system here, sort of a catch-up video for the stuff we did not get to in lecture. Talking about the different systems that regulate cardiovascular function. We talked about the baroreceptor system, which is the main regulator in the short term of cardiovascular function. There are some other ones as well. So there are a couple of hormonal systems that can regulate cardiovascular function. So the first one, and it's sort of pseudo-hormonal anyway, it's the renin-angiotensin-aldosterone system. This is a system that's the sensors are located in the kidney. So there are cells in the kidney that make a molecule called renin, and what renin does is there's a protein that floats around the blood all the time called angiotensinogen, made by the liver. The liver just secretes it into the blood, and it basically doesn't do anything on its own. When renin is secreted, renin is an enzyme, a proteolytic enzyme. It breaks angiotensinogen into angiotensin 1. Angiotensin 1 actually doesn't really do anything by itself, but then there's another conversion that happens. There's an enzyme, angiotensin converting enzyme, or ACE. It's actually found on cells in the lung, oddly enough. Anyway, so angiotensin floats around, comes into the lung. These lung cells have ACE. They break angiotensin 1 into angiotensin 2. And angiotensin 2 this is the signal that has quite a number of effects in the body. It's basically an important hormone. So angiotensin 2, its main effect is actually to travel to the adrenal cortex and stimulate the adrenal cortex to release aldosterone. And aldosterone has important effects on the kidney, particularly to increase the absorption of sodium. But angiotensin 2 has other effects as well. Increases thirst, increases sodium reabsorption in cells in general. The one I want to focus on now, though, the direct effect it has on the cardiovascular system, is that angiotensin 2 causes vasoconstriction. And actually, if you think about the name, angiotensin, angio means blood vessel, tensin means tension. So angiotensin 2 was discovered is by its effect that of causing constriction in blood vessels, particularly arterioles, increasing overall resistance in the body. And generally causing increased pressure, although as we learned in the last part where we looked at the cardiac and vascular function curves, clamping down vessels is not the most effective way to increase pressure, but it can have important effects of directing blood flow to different places anyway. Basically all the arterioles throughout the body except brain and heart have receptors for angiotensin, causing them to constrict. So what regulates the system? Basically, there are two signals that can drive kidney cells to secrete renin. One is if they detect low blood osmolarity, which is basically low blood sodium, most often anyway. that causes them to secrete renin. The other one is if they detect low blood pressure, right? So here's sort of a direct cardiovascular regulatory effect. They detect low pressure, that causes them to secrete renin, and that causes vasoconstriction. So this is sort of the short-term effect that where pressure can cause vasoconstriction through this system. As you can imagine, if renin secretion causes increased sodium reabsorption, that actually has a long-term effect of increasing blood volume. So that's actually one of the major ways. So I said like that in the long run, the system that has the greatest overall effect on blood pressure is actually the kidneys, and the kidneys' relative excretion or absorption of water. And so this renin system and sodium reabsorption leading to blood volume increase is one of the main ways that the kidneys can cause long-term increases of blood pressure. But it also has a short-term effect that works by low pressure triggering renin, which then triggers vasoconstriction. Then the last system, no, sorry, not the last system. So the last system for regulating pressure in the short run is another hormonal system, which is ADH, which what we said, also known as vasopressin. So and vasopressin has a sort of a short-term effect of causing arteriolar constriction and therefore increased TPR. Again, as always, heart and brain do not have receptors for vasopressin. They do not undergo constriction when vasopressin levels go up, but all the rest of the arterioles in the body do. So vasopressin, or ADH, actually has its main effect on the kidney, which is to increase water reabsorption. But its short-term effect is a direct effect on the cardiovascular system, increased arterial constriction, increased TPR. What regulates ADH? So kind of like the kidney, cells that secrete ADH respond to both pressure, so there are baroreceptors, and osmolarity, osmoreceptors. These guys are located in the hypothalamus. And then these baroreceptors, osmoreceptors synapse onto the hypothalamic neurons that then project down into the posterior pituitary. So hopefully you remember posterior pituitary basically is a bunch of nerve terminals of these neurons that live in the hypothalamus. So this is a neuron that makes ADH, sends its axon down and releases it here, and then a little blood vessel comes through, picks up ADH and brings it down to the body. So the regulation is through these receptors that live in the hypothalamus. So when increased osmolarity triggers ADH secretion, but more importantly, decreased pressure to the blood in the hypothalamus causes ADH secretion. So decreased pressure, secrete ADH, and then the short-term effect of arterial constriction, increase TPR. Again, that's sort of so this is sort of the short-term effect of this system. The longer-term effect, as with the renin, angiotensin, aldosterone system, the longer-term effect actually works through the kidney increasing water reabsorption, thus increasing blood volume. Okay, and we will talk more about those long-term connections between kidney and cardiovascular system near the end of the course. For now, we're focusing on this short-term effect directly causing arteriolar constriction. Finally, there's one more system that can regulate cardiovascular function systemically. And so it's a set of reflexes called chemoreceptor reflexes. So I should have probably put a slide in here, but so you'll notice here that there are chemoreceptors. So this is so this slide we use to show the baroreceptor reflex. We said that there are the baroreceptors in the big arteries, the aorta, and then the internal carotid artery that detect blood pressure. Blood pressure drops, they stimulate the medulla, which triggers increased sympathetic output. Blood pressure goes up, the medulla triggers parasympathetic output and decreases sympathetic. So there are also chemoreceptors located in the carotid body. There also are some in the aorta. And these chemoreceptors, they actually, so the receptors in this system, they sense blood, PO2, PCO2, and pH. Okay, so they're basically sensing blood chemistry, right? Chemoreceptors, O2, CO2, and H plus concentrations. So these receptors, these chemoreceptors, go back and talk to the medulla. Not exactly sure what structure of the medulla. It might be the same one that the baroreceptors talk to. So obviously, I don't know it. You don't have to know it. But so they talk to the cardiovascular centers of the medulla, and they regulate cardiovascular function. And it's not immediately obvious why O2, CO2, and pH levels should regulate cardiovascular function. It's obvious why they should regulate respiratory function, right? I mean, obviously, O2 and CO2 and pH are highly influenced by respiratory function. So you'd want those to influence your respiratory drive, and they do. But they also influence the cardiovascular system. And the basic idea is, so the respiratory system, needs to basically, bring more oxygen to the body, to the tissues when needed, get rid of more CO2 when needed, and then, so when you're under exercise, you need to be able to bring more oxygen to your tissues and blow off more CO2 than when you are at rest. So your lungs are going to need to do a big part of that, but so, when you exercise, you breathe more. But what else happens, right? What's another pretty obvious effect? So if you feel your pulse, you're going to notice that your cardiovascular system is working a lot harder when you exercise as well. And the reason for that is that your lungs don't, the increased breathing isn't going to do a lot of good unless you can transport those gases back and forth more effectively. And so basically, you need to accomplish exchange between blood and tissue to regulate O2, CO2, and pH. That's, they're needed in the tissues, or they build up in the tissues, and you need to exchange them with the blood to be able to move them to and from the lungs. And if you remember the exchange equation, exchanges, so to get, say, O2 into the tissues, you want to get as much of it as you can. So the amount of that you exchange is given by the exchange equation, which is Q blood flow times the concentration of X in the blood minus the concentration of X in the plasma. So for example, if we're talking about the exchange of O2, of oxygen, you want to get a lot of oxygen into, not blood, not plasma, sorry, this should be, should be X in tissues. So to get a lot of oxygen to go from blood to tissues, you breathe more to make the concentration of oxygen in the blood go up. But you also need to make Q go up, make the blood flow go up. To get a lot of exchange, you need a lot of blood flow. Okay, so in general, I'll tell you that the mechanisms, the actual mechanisms that connect blood chemistry to cardiovascular function are complicated, and there's a lot we don't know about it yet. And there's actually some debate about exactly what happens. But here are the general patterns that are observed. And it's kind of what you might expect. Increased PO2, decreased PO2, increased PCO2, or decreased pH all lead to increased cardiac output. So that's the effect they have on the heart. So rather than calling this one, I think I'll say on the heart, you have that effect, and then on the vessels, the same changes. You'll see increased constriction of arterioles in periphery, leading to increased flow to heart. To the heart, lungs, and brain. So this is what we're generally going to see. Now, but one thing that's kind of just important to emphasize is that, again, these systems are complicated, not that well understood, and it's not actually always obvious. So these patterns don't always follow, and sometimes patients will have kind of odd changes to blood flow when their chemistry gets out of whack. But in general, if someone's hypoxic, or if they have elevated CO2, or if they have low pH, so they're acidotic, then they're going to have, their heart rate's going to be going higher, beating faster, higher cardiac output, and their vessels peripherally are going to constrict. Okay, so that's all the extrinsic regulatory systems. So now we're going to talk about what are called the intrinsic regulatory systems. So by intrinsic, what we're talking about is systems that happen really at a local tissue level, not systems that come from some sensor that goes through some system and then sends signals out to other parts of the body. We're talking about things that happen directly at the level of the tissues. So let's look at this diagram. So we've got our arterial, and then we've got the arterioles leading into the capillary bed. We've got these precapillary sphincters, little rings of smooth muscle at the entry point to the capillary beds. Then we've got our capillaries. Our venules have a little bit of smooth muscle, and then veins. So the smooth muscle of arterioles is influenced by both all those extrinsic signals that we already talked about, but also by intrinsic, basically tissue signals. So there are signals that are released by cells in the tissues that can affect the smooth muscle of arterioles. So that's arterioles. Precapillary sphincters, turns out, are only influenced by intrinsic tissue signals. So the extrinsic signals that affect arteriolar smooth muscle actually don't affect the precapillary sphincters. These only respond to local tissue signals. But local tissue signals can have an amazing, very precise sort of control over where the blood flows, which pass through the capillaries, as we'll see. And just what I want to point out here, I kind of go through a little riff with an equation in the notes, but I think the main point I want to make is just that if you think about the blood flow, from arterioles and capillary sphincters into capillaries, and then veins. So you've got resistance in the arterioles and precapillary sphincters, which I'm calling RA. The capillaries have some resistance. The veins and venules and veins have some resistance. But the arterioles are the main set of resistance, right, as we know. And so the resistance, there's basically the tone of the smooth muscle here on the arterioles and precapillary sphincters is the major determinant for flow through, from arterioles through capillaries into veins. Okay, so let's talk about 3 patterns of local tissue regulation that are seen. So basically, these are ways that blood flow have been observed to change at the local tissue level. And then we'll talk about a couple of mechanisms and how those mechanisms can explain some or all of those different patterns. So, patterns of regulation at local tissue level. So the first pattern that we see is something called autoregulation. So autoregulation is seen here. So let's say we're measuring blood flow through an arteriole as pressure increases. Okay, so we're going to be so the x-axis arterial pressure is going to be this pressure. And then the y-axis is going to be flow through here. Okay, so we're measuring flow through the arteriole as pressure increases. And so what we expect is our old friend flow is equal to pressure over resistance. As pressure goes up, flow should go up in more or less a linear fashion. So this red line shows what you actually expect to see in an elastic vessel, in a hose that with some elasticity. It's not quite a line. As pressure goes up, you get this slightly curvy function. But pressure goes up, flow goes up. right? If we look at real arterioles, though, that's not what we see. We see that, under sort of in a low pressure regime, you basically see, that increased flow with increased pressure. But at a certain point, that function starts to severely drop off. In fact, it completely flattens out. And actually, really here is where we start what's called the autoregulatory range. And in here, within this autoregulatory range, increased pressure has almost no effect on flow. You get the same flow through the system regardless of what the pressure is. There's some limit, right? So as the pressure gets beyond a certain point, then autoregulation basically fails. More pressure gives you more flow again. But through most of the range of pressures that a lot of arterioles experience in the body, they live in this autoregulatory range where the flow through them is basically constant. And so it's been observed that the flow through arterioles and tissues tends to be pretty stable even as pressure coming through varies up and down. And that's basically autoregulation. Again, we'll talk about the mechanisms, possible mechanisms. There's still some dispute about it. But we'll talk about possible mechanisms in a moment. By the way, there's an error in my notes on page 4 near the top. It says, within the autoregulatory range, RA decreases as PA increases. All right, so there is actually a pretty obvious explanation for what happens here and what has to happen. So in here, as pressure goes up, flow does not change. So if pressure is going up and flow is not changing, so let's say pressure goes up by 10%. By this equation, pressure up by 10%, flow should go up by 10%. Unless what? So if this goes up, but if you want to keep that from changing, what do you have to do? To R, and that is make it go up. So within the autoregulatory range, as pressure goes up, resistance goes up, and vice versa. This is where my notes are in error. My notes say within the autoregulatory range, RA decreases as PA increases. That's wrong. So what we know has to be the case is for this to happen, that the resistance of arterioles goes with pressure. So if pressure goes up, the resistance will go up. Pressure goes down, resistance goes down, and that keeps flow through the arteriole constant. And that's how autoregulation works. Now we want to sort of say, well, why? And we're going to talk about that in a bit. But that's the essence of autoregulation. Resistance of the arteriole changes with pressure coming into the arteriole, keeping flow constant. These two change together. Okay, so that's a really important phenomenon at the tissue level. It's observed with arterioles all over the body. Second phenomenon that we observe is called active hyperemia. Why is this so messy? Anyway, so in active hyperemia, what we get is we observe that if you look at the rate of metabolism in a tissue and measure blood flow through that tissue, you see that there's this very clear direct relationship. As metabolic rate of the tissue goes up, blood flow through the tissue goes up, and vice versa. So it's called active hyperemia. Hyperemia means increased blood flow. So increased blood flow when tissue is more active than when it's less. and it's clearly happens because of dilation, basically. Arterioles. Ugh, God, it's very messy. Arterioles dilate more when metabolism is high than when metabolism is low, causing there to be more flow. When metabolism is high than when it's low, right? Because I know I'm sort of pounding this into the ground a little bit, but flow is equal to pressure or resistance. As resistance goes down, flow goes up. So arterioles dilate, flow goes up, right? Finally, we get what's called reactive hyperemia. So here's a good experimental demonstration of reactive hyperemia. So in this experiment, they are measuring the pressure in the femoral artery of an animal, and then blood flow through that artery over time. So this is pressure, this is flow against time. So what they did here is that, so they know this is sort of the regular pressure, and then here, actually at each of these 3 points, they occlude the artery, meaning they make the blood flow go down. So, it's sort of normal blood flow, then they occlude it, pressure drops, they release it, pressure goes back up. Then occlude it again for a little longer, then occlude it for even longer. If you look at flow through the vessel, you see, so here's the sort of normal flow. When you occlude it, flow goes down. When you release it, flow goes back up, but it actually increases beyond its normal level for a while, for a couple minutes, and then it comes back down. Occlude it again, flow goes up even higher, stays up for a little longer. The longer you occlude it, the higher the flow gets, up to a certain point anyway. And the longer the increased flow lasts. So this increased flow is the hyperemia, and now it's reactive because it's reacting to a previous decrease in flow. And again, we know that at these points we're having dilation of arterioles, and actually I should also say plus precap sphincters, and that's also true for the other ones as well. So both arterioles and precap sphincters change their resistance in all three of these phenomena. And one of the important points to make about, so you might be thinking, well, you haven't proven that this is, you started by telling me that this is a tissue level effect, but you're just showing the effects. You're not, I don't know that this isn't happening at some systemic reflex. So all three of these effects can be observed on like organs that you take out of the body and artificially keep alive by perfusing with blood. Again, obviously in animals, but you take an organ, take a body part out of the detach it from the rest of the body, keep it alive by providing some artificial circulation. You can see all these effects when that part of the body is removed from the rest of the body. It's not a systemic effect. It's not reliant on systemic circuitry. It's all happening at the local tissue level. So what are the mechanisms? Again, it's not fully understood. So patterns. So sorry, let me continue my list here. The patterns of regulation that are seen at the local tissue level: autoregulation, active hyperemia, and the third one was reactive hyperemia. Okay, and then now let's talk about mechanisms that may explain one or more of the above. So there are a couple of mechanisms that are known to happen in local tissue level, and we'll talk about, like, you know, which one of these, which of these phenomena could be explained by the mechanisms we're going to talk about. So there are two mechanisms that are known to happen at the basically arterial or in precapillary smooth muscle. One is called stretch activation. So, and what we find is that these smooth muscles on arterioles and precapillary sphincters, stretching them causes them to constrict. You can see that here in the renal arterial, arteriole, increased renal arterial pressure gets increased arteriolar resistance, and this is a direct reflection of this stretch activation. Your higher pressure, stretching them more, stretching the arterioles more, they constrict more. So pretty much all arterioles and precapillary sphincters have this stretch activation. In fact, a lot of smooth muscles do. It's a common property of smooth muscles in any organ. So increased stretch, increased constriction, and in the cardiovascular system, what that would equate to is increased pressure, increased resistance. So, which of our regulatory processes could that explain? Well, one where it could very clearly explain is autoregulation, right? I mean, we said the essence of autoregulation is that in this range, as pressure goes up, resistance goes up. So we said that, you know, if you increase the pressure here, you increase the resistance here, and keep flow constant. And that's exactly what stretch activation of the smooth muscle would give you. So it's clearly an important part of autoregulation. How about active hyperemia, increased metabolism leading to increased flow? And people have tried to make some sort of roundabout explanations, but it's not really clear how that would work, how stretch activation would contribute to that. Reactive hyperemia probably is important in the following way. So, under high pressure, normal high pressure, you have high resistance of the arterioles, right? High pressure gives you high resistance. When you occlude the artery, the pressure goes down, makes resistance go down in the arterioles and precapillary sphincters. And then when pressure returns, it takes a little while for the resistance. So it takes you know, the blood flow returns. Resistance initially is still low, and then the little guys all start constricting, bringing the pressure back down, or bringing the flow back down, I should say. Again, so by the time, so at the beginning here you have low resistance, but then you get back to high resistance by the end, and then you occlude it, you get down to, you get drop in pressure, drop in pressure, leads to a drop in resistance again, but then you restore it and you start off again with low resistance, but after a little bit of time, resistance comes back to normal because you're doing things, stretching them out. Pressure is high again, you stretch them out again, resistance goes up, and then ditto. So same thing happens, this third time. So it's basically, you could just say that this increased flow after a period of occlusion is just basically the time it takes for the muscles to start to constrict again after they, so the muscles are constricted, and then the muscles relax, and then it takes them a little time to constrict again, and then they constrict, relax, they're still relaxed, but then they constrict again, etc. So you can see how stretch activation would be a feasible explanation for reactive hyperemia. Why does stretching smooth muscles cause them to constrict? And basically, it's been shown that smooth muscle cells have stretch activated cation channel. So it's a channel that that opens when the muscle cells are stretched. The equilibrium potential for these channels is about 0 millivolts. So it causes depolarization of the muscle cell and therefore increased tension. So you stretch a smooth muscle cell, you open these stretch activated channels, depolarize them, cause them to constrict. The other main mechanism that you see at the level of the tissue is what we call the local metabolite response. Gosh, I got better handwriting here. So, there are a bunch of molecules that are produced by cells in the tissue that can affect the tone of arterioles and precapillary sphincters. So these guys here are all molecules that are produced or present at the level of tissues, not necessarily produced by the cells themselves in some cases, but anyway, they're present at the level of tissues. And all of them can affect tone of arterioles and precapillary sphincters. So we've got oxygen, CO2, potassium, acid, basically any acidic molecules like lactic acid, for instance, and adenosine, 5. And of those, all are vasodilators except oxygen, which is a vasoconstrictor, and that'll all make sense shortly. So these are all the what I call metabolites, molecules that have to do with metabolism. There's actually a whole other range of molecules that are immune signals that also affect blood flow, and in fact can be are responsible for the very notable blood flow changes due to infection, for instance. I'm sure you guys have seen or maybe even experienced cellular response, sort of skin responses to infection that cause increased blood flow. This happens very commonly with infection. We're not going to talk about the immune signals because they're complicated and not directly relevant to sort of general physiology, at least as far as I'm interested. But so the idea is that all these metabolites up here, actually all these molecules, but focusing on the metabolites, the smooth muscle cells have receptors that detect these molecules and cause them to either dilate for these guys or to constrict in the case of oxygen. So they actually detect the presence of those molecules and change their tension in response. Okay. And so what you notice is that so I'm going to call these four, by the way, I'm going to refer to these four as metabolic wastes. I hate when I do this. Okay. Wastes. The reason I'm calling them metabolic wastes is that they're basically all generated by metabolism. The more you metabolize, the more CO2, the more potassium, there will be the more acids, things like lactic acid, and then also just CO2 making acid and adenosine. All of these are produced at higher amounts when cells metabolize more or when they're deprived of oxygen. But let's just think about them all as being metabolic waste. More metabolism, more of these guys. And then oxygen's the opposite, right? More metabolism, so for the metabolic waste, more metabolism leads to more metabolic waste. Oxygen, more metabolism leads to lower tissue PO2. So, under conditions of high metabolic demand, you have high metabolic waste, low PO2. So the primary effect is you get lots of these molecules, not much of this. So the overall effect is dilation and low metabolic demand leads to low metabolic waste, high tissue PO2, and the overall effect. So low dilators, high constrictor, you get constriction. Okay. So the local metabolite response, high metabolic demand leads to dilation, low demand leads to constriction. Which of these phenomena can be explained by that? So, starting with autoregulation. So you can kind of explain it a little bit, just because, if pressure goes up, theoretically you may be having a little more blood flow initially. So O2 levels will go down. Sorry, hold on a second. Sorry, let's actually think about it. Let's think about maybe the other way. So imagine as pressure goes down, blood flow kind of goes down. Metabolites build up, oxygen goes down. So metabolites cause dilation, right? So as pressure drops, you can imagine that initially you get more metabolites, causing resistance to drop. Get dilation and resistance drop. So lower blood flow, initial increase in metabolites, decrease in resistance. So pressure drop, resistance drop, and vice versa for pressure going up. But it's sort of a roundabout explanation. So it's not generally considered to be a very important mechanism for autoregulation. How about active hyperemia? Metabolism going up, blood flow going up. That would probably be pretty easy to explain. Thinking about metabolites, and that seems to be the main mechanism here. So this effect of metabolism on blood flow is thought to be primarily due to the presence of tissue metabolites and their effect on tone in arterioles and precapillary sphincters. And ditto for reactive hyperemia. When you cut off blood flow, you're increasing metabolic waste, decreasing oxygen, and so therefore when you restore blood flow, everything's dilated and you get a big surge in blood. And then just the last point I want to make here is just talk about, sort of the cellular basis again. So so if this is the arteriole and precapillary sphincters, we've got muscles here. So, and these cells, the muscle cells, smooth muscle, have just receptors for oxygen and metabolites, and when those metabolites are present at when the metabolites are present at a high level, they cause this diagram is supposed to be showing, cells that are at rest. And then they increase their metabolism. They soak up more oxygen. They put out more CO2. Those molecules are detected. The CO2 and lack of oxygen are detected by the smooth muscle, causing increased blood flow to basically, provide more oxygen and suck up more CO2. So how exactly does oxygen and metabolites affect the tone of these smooth muscle cells? Complex transduction mechanisms not well understood, basically. So that's about all you need to know about that. All right, so that does it for this lecture. Thank you very much.